Now that we understand how to make EER diagrams, it's time to look at some of the options to model inheritance in a relational database. So we're going to convert those EER diagrams to physical models in this lesson. Relational databases do not allow for inheritance. So how can you take an object-oriented structure and work it into a relational schema? And there are three ways to do it, three main ways, and they're listed below. The single table per class hierarchy, the joined subclass strategy, and the table per concrete class strategy. One of these concepts involves a concrete class. That should be familiar to you from object-oriented programming. But a concrete class is a class that was designed to have instances of, whereas an abstract class is a class that is designed to be a blueprint but never to create an instance of. So for example, if we had this hierarchy, we know we're going to make student objects, we know we're going to make instructor objects, but will we make persons? And we might use the person class for a generic person like a staff member. Or we might say, no, we only want to have students and instructors, in which case person will be abstract. So when we look at one of our strategies, it's a table per concrete class. And that means that we actually plan to have instances of those data elements. So here we have a classic inheritance structure. We have the generic item, and an item consists of its subclasses. We have books that are items, and we have CDs that are items. Those are the two subclasses. Books, you understand, have an ISBN, a publisher, number of pages, and illustrations. CDs, in case you don't know what those are ways to store music files and play them on a disc. The CD was the disc. I think you can still buy them today. But in any event, when we used to have them, you could have a music company, the number of CDs, you could have a 2 CD set, the total duration of the CD, and the release date. So those are the subclass fields that we are storing or interested in databasing. If we look back up at the superclass, everything, whether it's a book or a CD, has a unique identifier, it has a title, it has a price, and it has a description. So that's how this hierarchy works. Now we're going to see the three different ways to model this in the database. The first way to model is a single table per the class hierarchy. In this case, you take the superclass and all of its subclasses and you collapse them into a single table. So you'll notice that here, from ID down to description, these are the superclass fields of item. And then we have the 4 book fields. And then we have the 4 CD fields. And this is a way to have all the information in one table. This table we'll call item, because it will contain all different kinds of items. Now, the advantage of the single table per class hierarchy is that all the information about items, books, and CDs is all in one place. This means that you will not have to do any table joins to find information. Joins in a relational database tend to be expensive, and so this might offer the most efficient way to store information. However, it does mix and match lots of things. There'll be lots of null columns. All the CDs will have nulls for ISBN, publisher, number of pages, and illustrations. All the books will have nulls for the music company and the number of CDs, etc. So you're going to have a lot of sparsely populated columns, and that's something that we don't like to see a lot of the times. The other thing that's discouraging about a single table per class hierarchy is that there's no differentiation. I guess you assume it's a book if you see an ISBN number. I guess you assume it's a CD if you see the number of CDs field. That's not a good way to handle this. And so you'll notice that in red, there's this field called D-type. D-type is an optional field in this inheritance model. D-type stands for a discriminator, and it's just a field that says what kind of type the item is. So for example, it might say book, or D-type might say CD. And that's a way for you to subdivide this giant table. The other issue with this table is that it doesn't appeal to our sense of organization. It mixes books and CDs together, and maybe we want to have them separate. But again, the single table per class hierarchy is the most efficient way to model this information, but it is the most wasteful. The second way to model this inheritance is with a joined subclass model. This is probably what you're familiar to in object-oriented design, where you have a superclass that has superclass fields, and you have subclasses that have subclass fields. So notice here we have all three tables. We have an item, we have a book table, we have a CD table. And the superclass fields are all here in item: the title, the price, the description. Also notice that we have the ID of the item in the item table. Now, in Java, you could inherit the superclass fields, but there's no real inheritance in relational databases. So that means that we're going to have to repeat the ID in each of the two subclasses. This way we can connect a book to its item record. So for example, take the book It by Stephen King. The item field might have the title of It, and the book might have the ISBN number for It by Stephen King. So if I wanted to find all the information about It by Stephen King, I'd have to take the book table and join it to the item table using ID. What's cool about this is that in the item table, ID is the primary key. In the book table, ID is also the primary key, but it serves a second purpose. It's a foreign key. So ID in the book table and ID in the CD table are both primary keys to their own table and foreign keys back to item. So what are some of the advantages of this? Well, the advantages of this are that it's organized, everything's in its place, it's a common way for us to represent inheritance, and there's no wasteful space. The books have all their book fields in the book table. The CDs have all their special CD fields in the CD table. And the item table just contains the superclass fields. Now, a downside of this is joins. You have to always join the item with the book or the item with the CD in order to get full information, as we described earlier. The more joins you have to do, the more expensive the operation is in terms of efficiency. However, you have to look at what we're doing with each of these fields. For example, do most of our reports, do most of our queries, are they just focused on the titles and the price and the description? If that's the case, then you could limit your queries to the item superclass. So the question is, how often do we have to dip down into the specific fields of book and CD? The less often we have to dip down, the better the joint subclass model works, because we will avoid some of those joins by staying in the item table. Notice that there's also an optional discriminator field, D-type, and the D-type would again store book CD. You don't need this field because you'd be able to join to find out if an item was a book or a CD, but having the discriminator there is often a good way to quickly look at the item table and know what kind of item it is. There's another interesting complication to the joined subclass model, and that has to do with the IDs and keeping them in sync. In both the single table per class hierarchy model and the table per concrete class model, you can just have the ID, the primary key, be an auto increment. But not so in the join subclass model. In the join subclass model, the superclass table, the item table, can have its primary key ID be auto-incremented. But none of the subclasses can use that strategy. The subclass has to match the superclass's ID, so that the primary keys for book and CD and any other subclasses cannot be set to be auto-incremented. This typically means you have to write special database programs to retrieve the ID of the newly inserted item and to use that as the primary key in the book and the CD. So there's a bit more administration to make the insertion of records work in the joined subclass model. In the table per concrete class model, all of the subclasses have all of the fields they need to fully describe a row. So for example, the book table has the superclass fields of title, price, and description, and then it has its own unique fields of the ISBN, the publisher, the number of pages, and illustrations. The CD table also has the superclass fields of title, price, and description, and then it has its own fields for the CDs. So in effect, this is like a one-stop shop. If I go to the CD table, everything I need to know about it is in one place. If I go to the book table, everything I need to know about a book is in one place. In this model, you have IDs, but the IDs no longer need to be associated with a superclass. So the book and the CD table can auto-increment their ID fields. Now, let's look at the item table up top. So the question is, do we need an item table? And that depends. That depends on whether you would have made item an abstract class or a concrete class. If you said to yourself, no, we are never going to have just a generic item, it's always going to be a subclass we're going to make, then you do not need the superclass table. However, if you are going to use the superclass table for more trivial items that don't need subclass fields, then you would make an item table. For example, let's say in your store you're selling books and you're selling CDs, and books and CDs have these important fields to keep track of, but you're also selling posters, rock and roll posters for the wall. These posters don't need their own special fields. All they need is the title of the poster, the price, and a description. In that case, if I were to have an instance of a poster for sale, I would make it in the item class. So the real question about whether to have the superclass table or not is whether you would ever have an instance of an item. And if you did, you would put that poster into the item table with its own ID, again auto-incremented, and a title, price, and description. So if you're going to use items, then it becomes a concrete class, and therefore you have a table for it. These IDs have nothing in common with each other. They are all the primary keys of each of their respective tables, but none of them act as a foreign key. They are all independent. So what are the strengths and weaknesses of the table per concrete class model? Well, one of the strengths we've kind of alluded to, it's a one-stop shop. If you go to the book class, you'll find everything you need about the book, and that's nice. If you go to the CD class, you find everything you need to know about the CD, and that is nice as well. But if you ever want to work at the superclass level, this becomes very difficult. There is no true superclass field here. There's just an item table for records that don't fit into any of the subclasses. So in order for you to get your full inventory, you have to query the item table and union it with the book table and union it with the CD table. So you have to create a union query of all the subclasses and the superclass if you have it to bring the records back into one query result. That's going to be the most expensive of all. So you have to ask yourself the question, how is my business working? If my business is divided into units, like for example, there's a book department in Amazon and they just care about books. And then there's a music department and they just care about CDs. And very, very rarely do we ever have to have a query that runs across both tables. Then the table per concrete class model is not a bad one. But if I have to work at the superclass level a lot, where I want to see books and CDs as part of my query results in the same query, then the table per concrete class model becomes very expensive. Also, this is a minor problem with the table per concrete class, but we're repeating the title, the price, and the description for every subclass. That means that when we build a table, we have to build those fields 3 times for the superclass and the 2 subclasses. And if we had 100 subclasses, we'd have to build those fields 100 times. And if we had enums on them or validation rules on them, we'd have to do that for every single subclass. So the bottom line is that all 3 of these are viable inheritance models. Which one you use depends upon the priorities, the efficiency you need to gain, the way that customers are going to use your application, and hopefully you have enough insight to know the strengths and the weaknesses of each approach.